Right. Hello. Last talk. Are you? Hopefully this is an easy one that should go down relatively quickly. So, hi, I'm Dave. My talk is All You Need Is Pi. If you saw Mark's talk about how you have multiple items to do all this, now all you need, one of these. It's just a Raspberry Pi for most of the hardware hacking stuff. So let me just. So this is about, there's some basic hardware hacking. So an introduction to understanding some protocols, how you work out what a 1 and a 0 is. And to prove that you don't really need stupid amount of things to do this. So, for example, if you get into hardware hacking, you can have loads of stuff. There's a shikra, and there's a bus pirate, and all sorts of, USB PC converter. The thing I wasted most of my money on at one point was something called a hard exploit, which I spent about 100 quid on, and have never used because it never really worked. Don't buy it; it's a total waste of money. One of the things I'm going to say is what's wrong with using, say, a BeagleBone Black or a Bus Pirate? There's nothing wrong with them. If they work, they work. I just used a Pi because I had one in the cupboard, basically, when I was going around and using it. And basic lesson is, if you understand how these things work, it doesn't matter what you use. Use an Arduino, use a Pi, use a BBB, Odroid 2, any of these sort of embedded things. So, Weeble and Bob joke, just for obviousness. Pi! So, I don't normally do an introduction, but I sort of want to make a point here. So, I've been doing IT security for about 15 odd years. Originally, I was a developer, then did Unix sysadmin. My only hardware training was doing CDT design technology back in 1990. And pretty much all I can remember from that is Ohm's Law, a really offensive way of remembering resistor codes, which I'm not going to repeat. And that use a 555 timer for everything. I started doing hardware hacking because I started messing around with various different IoT devices. Started with the Kayla doll, which you might have seen on our stand, and then actually getting into looking in depth at how this stuff worked and what I could find from it. I've also got an interest in retro computing, i.e. stuff from when I was young, so there are a few references to that in this talk. Out of curiosity, that's my avatar. This is the full thing. You can see it's a Furby. This is generally what happens when I take hardware apart. It tends a tendency to explode. Actually, that one was, we set fire to it because it was funny. Oh yeah, that's from me when I used to have long hair, and that's a cloud pet, and I just thought it'd be more interesting to use as a glove puppet. Your choice. So, why did I choose to use a Pi for this rather than all the different things? It's small, it's cheap, you can get one for 25 quid. I'm using Raspberry Pi 3. You can get Pi 0Ws for it a lot cheaper. There's lots of general GPIO pins that you can use. Everything supports it. You can get a load of the drivers by default. More importantly, I had one sat in my cupboard doing nothing. In fact, I've got a load of computers stuck in my cupboard doing nothing. And it got loads of potential. You see, it's a tiny little board. This is a case I prefer because it has access to all the GPIO pins. Right, I'm going to start off with a quick demo. Now, technically, I'm going to break the law twice here. Once in radio performance rules, because, you don't have a license. And secondly, I'm going to do some broadcasting, which is technically illegal. Let's just say it is illegal. So I'm going to just switch over to my Pi before I do anything. There's my thing. So I'm just using the Pi through a normal Ethernet connection. Okay, my Pi is not booting. Let me just reboot my Pi. This is not a good start. This is where the demo things fail. It worked perfectly every time I tried this. Sorry about this. No! Yeah. Sometimes if you have a GPIO pin connected when you actually power on, it goes a bit silly. Right. So I'm just going to turn the radio on, and I'm just going to broadcast over Radio 1, home of banal music everywhere. Whilst I'm doing it, there is a sort of, I don't have my pointer here. If you might notice the error is a bit stubby, because while testing this, I accidentally turned it the wrong way and broke it off. So this is emergency cannibalization aerial, and I'm not actually... Great, I'm getting no signal, that's why. Yep, I'm getting no signal. I'm going to have to just broadcast over it anyway. So one of the nice things about a Pi is it's got a PWM chip in it, which is a pulse width modulation, which will basically, you can use to send stuff at various frequencies. So one of the nice things is you can actually broadcast stuff from the Pi. This is now not going to work because I can't get a radio signal, but let's try it. Oh, sugar. That's better. Oh, if you can, so you can hear a bit of Sabbath coming from there, but it would have worked a lot better if it's Radio 1 actually playing. Oops, now he gets radio. So that demo really failed. There is actually a modification where you can send stuff to the radio text stuff on that. So radio text is a subcarrier frequency that you can also send text to. So I can actually, instead of just playing over Radio 1, I can just send messages to the people listening to it. So hear them say, any old stuff. Now, one of the nice things about the radio subcarriers is, have you ever heard of something called TMC? Which is Traffic Management Control. So all those things on your sat-navs that you get where it goes, there's an accident at junction 21 of the motorway, avoid. Yeah, you can write to those. It's unencrypted. You could say, zombies here, avoid. Unfortunately, I couldn't get that demo working, so that's one that never got. So that was technically legal. Fortunately, there's no signal in here anyway. Most important thing to go on to is, how do we take something that's hardware, something that's got the physics of how things work, and how we translate them to bits? How we make sense of it, how we do all that sort of thing. What's a 1, what's a 0, what's just noise. There are many ways of doing it. One way of thinking of it is about Morse code. So in Morse code, you've got dis, you've got das. So you've got basically timing scopes. So if you've got a sort of time frame, you can sort of work out what a 1 and a 0 is. So let's go back in time. And that's a plot. Does anybody know what that is? A plot of? That's, okay, obviously no. That's a sample from a tape file from a BBC Micro Elite file. Just zoomed up a bit, that is 4 bits of BBC Micro Elite and how it would actually turn out to be a WAV file. So what I've done here is I've just done a couple of ones, I've done a couple of extra ones. So in the specification, a wave at 240 Hertz, 2400 Hertz is a 1, and at 1200 is, you've got 2 waves, is a 0. So we can actually work out how to make sense. So if I just add some annotations to it, so we can see the sample points there where the little arrows are, and just the separator to show where the bit patterns are. So we can see the first one is a 1, so we've got 2 waves there. A 1, anybody guess the next? Yeah, and a 1. And that is basically the fundamentals of 1980s computing and how to read and write to data. So let's go into digital. It's a lot easier on digital. This is an example of an SPI protocol. And we have 2 data lines which are shown. One's got an enable which says the direction of traffic, and a clock. So as you saw, if you saw Mark's one, when you have a clock change, it tells it to read a sample. So in this case, I'll do the same breaking out on it later. Here's 1 byte. There's your sample points on when the clock rises. And there you can see the bytes are a 1, a 0, a 1, and you can generally guess the rest. That's fundamentally what we do. It's really simple. So the title's a bit wrong there because I added this right at the last minute. So this is the Raspberry Pi GPIO header. This is how it is. So you've got 40 pins on it. Some are designed to specific things. A lot of them are power points, ground points that you can always tap off. They're quite useful throughout, but the numbering in the scheme's a bit weird because that's how it numbers internally. So that's why it goes from pin, your GPIO pins, like pin 2 sorry, you've got 17 and 18 in weird places, and then 17, 27 is just below 17. So we're going to just have a look at some protocols here. So I'm just going to swap my pies to, here's one I prepared earlier. So UART is a very simple serial protocol, which is often used for consoles and stuff like that, which you can easily read on the pie, but there are two UARTs that are built into the chip. There's a hardware UART, which on the Pi 3 is tied to Bluetooth, which I don't want to touch because I like having Bluetooth in the Pi because I can use that for other things. And there's a mini UART, which is got a few features that the major one doesn't do, but it will still work. I just need a custom cable. There we are. So this is a Broadcom router, not Broadcom, it's a GL iNet router, which has a convenient UART connector onto it. So I'm just going to connect here and hope that it doesn't bounce. So I'm connected pins 14 and 15, which are RX and TX, and the ground, and my mouse has just clicked on the right mouse button. And I'm just going to power it on, so just reconnect and hope it actually reconnects. This is not the time for my pies to fail. Can you actually read that? I'll just do a zoom. Typical zoom. Right, so I'm just going to... Great. I'm sorry, I'm having... I thought the problem with this was actually the Pi power supply, but this should be running full voltage. This is why you never do live demos. Because everything dies. Yeah. Okay. That's not working. Sorry. I do apologise. So that's not going to work. Fortunately, I've got a screenshot. So you're connecting pins 14, 15 and ground. You need to cancel the default Getty because the console also runs that port. So you need to cancel. You get weird stuff happening. So that's what you end up doing, which is a screenshot of what I was just going to demonstrate. So this is your UART terminal of the actual thing. So rather than actually having on a PC, you would have a serial board like that. You'd have to use that to plug in. This one, just one little cable. But the more interesting stuff is trying to read firmware. So this is a thing that we do all the time in trying to do it. Andrew's shown you ways earlier of trying to extract stuff from microcontrollers. This is the actual firmware chips itself. There are multiple ways of actually talking to these chips. Different protocols, SPI, I2C, microwire. And the most common ones you see are SPI and I2C. So these all have their own way. This is, on the right is what is... sorry, brain stopped. It's got a laser on it. Yeah. You've got a typical SOIC or SOP layout which shows how I2C works. So it's basically two simple wires, SCL for a clock, SDA for data, and you've got a load of address pins which may or may not be needed. Depends on how configuration is. And there we have, that's roughly what the package for I2C looks like. Is that laser? No, it isn't. So, second line down you can see is obviously a clock. Top one is actually where the data is. And it's relatively simple. Everything's byte-wise. And to read data, you have a control code, set a few bits, send that packet out, data comes back on SDA. It's a really simple process. I'm not actually going to demo this live because my chips... Oh yeah, I actually have my control. There is a chip in there. But with the current problems I'm having, that one might sometimes be a bit flaky. So I'm not going to actually demo this one. I'm just going to skip to SPI, which is the most common one you'll find. You can have quite large amounts of data on SPI chip. which is quite common you'll find on this, the actual the GL board actually has the SPI chip there. You probably can't see it, it's that tiny little chip there. 8-pin chip. It's nice thing about it is there's a standard called JEDEC standard, which has a load of set bytecodes you can work. So it works on a simple bytecode system. I am going to attempt to read this one and hopefully show you how it works by actually entering some raw JEDEC stuff in. So I use clips basically to make life easier, and they just clip onto the chip individually and get into the right place. So I've put that in, and if you notice the board is turned on, because I'm actually feeding 3 volts through to the chip, and that's actually going past to the board and actually semi-booting it. Just make sure that's not powered right. Where's my movie turn? Here it is. I'm just going to restart the session, and hopefully I'm running out of space. Come on, boot. This is not going well. Yeah, I'm really selling this, aren't I? Aha! So, just as a demo of the actual how it works is on. So I've got a tool here which is basically a pretty raw version of the SPI one, so I can actually issue raw byte commands from here. Terminal zoom. So one of the basic commands is an RDID command, which basically says identify the chip. So I've just expanded it slightly to show you what the actual bytes are. You can see it's in a 9F byte, which is basically the opcode for ID. And it comes back with the actual data, and it tells it got a firm grasp on that chip. Let me just reseat that. Do you know the most annoying thing about this is when I was trying this out there, it worked perfectly every time. Yeah, I got it the right way around. Ah! I have done this on millions of boards and millions of different things. Yeah, finally it works. So that there is what we call, comes back from the RDID, which is the density, i.e. the size of the chip, and the manufacturer, which is a lookup code that you can then look up and do. If we want to read some data, let's just read 100. Read 100 bytes, which is not working. Great. Never do live demos. Right, fortunately I took a screenshot earlier. So that was how to do it, custom one. That is what's meant to have come back, where you can actually see there's actually data in that. So the packet goes out, says read, which is a code 3, 64 hex, which is 100 decimal, and then 64 byte. Those are the first 10 bytes from there. Right, this is going to be a demo. So when you normally read from a chip, you normally use a program called FlashROM. FlashROM is great, but its interface requires you know a few things beforehand. You got to choose the chip exactly. You got to know what the chip it is. You got to have the right pattern. If it doesn't understand the chip, it won't read it. And you're on your own then. You've either got to edit the source to edit your own definition to it, or you can read it itself. And also, if you want to do a partial read, you've got to write a definition file, save that to disk, load the definition file in, and it's a pain in the backside. You can't just say 0 to 1, 0 to 100. So I've actually got a bit of code that I wrote, which I need a better name. I called it SPI Reader because I'm not very excited at thinking of names. and it is literally a one-click read for SPI through a web browser. So just to make it easy, now if I can get this working, it should do this fine. So where's my Moby term? Actually, sorry, let me just go in here and make sure I can read. Yes, I can. Right. So that just opens a web browser on 5000. So for example, am I allowed to swear? Stupid thing. Seriously, I have no idea what's going on at the moment because it's really annoying me. Yeah, I think I'm going to need it. Then we want to see me get drunk and sing bawdy songs. I mean, that's probably going to be easier. Right, I'm going to use the other pie. There is a reason why I took 2 pies and the software's on both of them, just in case this happens. Yeah, I don't have generally a good history of talking in demos because they generally always fail on me. Right. That's why my clip has got a bent pin. It sounds painful. Right. Nope, that's not it. Okay, I don't have it. Oh. No, I don't have it on this machine. Damn it. I am being cursed today, sorry. It would have been sensible if I just used the same card on both, wouldn't it? Right. Sorry. Right, let's try again. Yay! I can read it now. That's better. So, as you can see, the identifier, the routine adds a bit more, so it actually decodes what the manufacturer chip is. But that's just the identification. So let's do the easy read, and I'm now going to make myself look silly if this doesn't work. So here's the interface. Does anybody want to actually press that button to see how easy it is? Oh, I'll do it. So, and as you can see, it's going up, and that is reading your chip. Instead of having to remember a load of things, just swear lots of your pie and it eventually works. Because I'm trying to do a demo, damn it. So that's basically, you can read your chip like that, it will just download to a file. And that's relatively how simple it is. So anyway, you know I said I was into retro. This is another demo. So I have a load of old computers in my garage. Which I occasionally try and mess with. One of them was an Oric, which I got and never worked. So one of the things that they said for checking on a number of different things is check the EPROMs at work. So this here is the high 8K of an Oric ROM. It's 35 years old. It's probably older than several people in this room. And I just went, as a challenge, can I read this? So it's a very simple process. Unlike all the rest of them, it's a parallel read. So you write an address, set your address lines correctly to an address you want to read, and then just read the D lines. None of this messing around with clocks or anything like this, just write and read. So we're going to attempt to do it through the browser. Again, This is a complicated one. As you can see, it's one of the difficulties is it's 28 pins. I had to make a separate board for it because you've got 28 pins, of which 27 need to be connected. Sorry, 27 need to be connected. And as you can see, it's quite complicated, the connector. It's normally meant to work from 5 volts, but I found that the 3 volt output should work. So, assuming that hasn't actually reset my Pi and it all works, we should be able to run this. Oh, I might have actually got the oh, sorry, I'll go to the command line version. Sorry? Did it? Oh, it actually worked. Wow. I'm so surprised something actually worked. Right, let's open that in HexEdit. And there you are. That's a chip that I've just read from a 35-year-old EPROM. If you know 6502, you can probably read that. But there you are. That's relatively how simple this sort of thing is. And that pretty much is it. But I'll sort of race through that one, sorry. Any questions? Other than technology, it does work, honest, Rob. There's a computer released in 1981. Were you even alive?
Infinitely inferior to a VIC 20.
It's infinitely inferior to everything, to be honest.
You got any good references to sort of learn that?
For learning general hardware hacking stuff is one of the problems is trying to find all these. The advantage of the Pi is most of the libraries are there. So the SPI reader and I2C reader, those are using common Python libraries. The actual Python to do it is a few lines of Python. You got if you look in the GPIO library, most of the things are based upon that. So you've got GPIO, you've got SPI based off that, you've got SMBus, which is an I2C reader. In terms of the actual EPROM stuff, yeah, good luck. Most of the people who know how to write EPROM, do this sort of thing, know how to do this sort of thing and don't tell people, or they think that everybody knows it. So, but the SPI stuff is already there. It's pretty much you have to go and find the data sheets. And the data sheets have the information in. It's just trying to work out what they actually mean by the information, because the data sheets are written for electrical engineers. So, yeah. Data sheets are the easiest ones. Always look for the data sheets. Any other questions? Before I now go and throw my pies away because I'm getting irritated with them. Maybe I should have got a BBB. Andrew's just giving me a look here just to say, told you. Yeah. Sit then. Let's get you quick.